My name is Felipe. I come from the University of Delaware. And in this talk, I'm going to present a new method for simulating open quantum systems that is non-perturbative, meaning it can handle strong coupling to the bath, and it's also non-Markovian, so it can handle systems that have memory effects. And this method is based on the Schwinger-Keldysh field theory, which is the field theory of non-equilibrium fields. To make discussions concrete, I'm going to focus on these two models, and I'm going to develop the theory for these two models. The first one is called the spin boson model. It's very paradigmatic in the field of open quantum systems, and it contains a single localized quantum spin coupled to infinitely many bosonic modes, whose frequencies are distributed according to some spectral density function. In this work, the spectral density functions that we're going to consider can be characterized by the low energy behavior as subohmic, ohmic, and superohmic. Even though this is already a complicated model and contains very rich physics, we will nonetheless generalize it to include many more spins interacting between themselves and many more baths to which the spins can couple to. This model shows up across many subdisciplines of physics, including quantum computing, where the spins correspond to the qubits, various branches of magnetism, and since we've been talking all day about atoms and cavities, it can also correspond to any two well-separated levels in an atom. Good, now onto the theory. I'm only going to give you the ingredients that go into formulating this theory. I'm not going to delve into the technical details, but if you're interested, I'm more than happy to talk about that later. The first thing we're going to do is we're going to map the spin operators onto Schwinger bosons. The reason we do this is because the canonical commutation relations of the bosons are more amicable to the field theoretical treatment that we want to pursue. We can use any number of flavors of bosons to do this mapping. We can map spins onto 2 spins, onto 3 spins. For computational complexity reasons, I'm going to map spin operators onto just 2 flavors of bosons, but nevertheless, 2 flavors are enough to capture any spin length S. Depending on the specific Hilbert subspace that we pick, we will be mapping a different spin. If we're in the 1 boson subspace, this is a spin 1/2. If we're in the 2 boson subspace, this is spin 1, and so on. As long as we're satisfying, this, the so-called Schwinger boson constraint, we can be sure that we're within the correct physical Hilbert space of the spins that we're interested in. And finally, I want to emphasize that n, the number of Schwinger bosons that we use to map the spins, is a mathematical detail and not a physical parameter. This will be quite important later on. Okay, once we do this, we recast the Hamiltonian onto the Schwinger-Keldysh action via the bosonic coherent states. This action is not defined on the timeline, but instead on the closed time contour, which goes from the initial time to the future and then back, which sounds kind of esoteric, but it's just a way to conceptualize how expectation values are computed in general non-equilibrium situations. The action goes into the generating functional, which integrates over all possible configurations of the field, and from which we obtain expectation values via functional derivatives. Now what we're going to do is various Gaussian integrals. A lot of field theory just turns out to be Gaussian integrals. The first thing we do is integrate out the environment. So we get rid of the bosonic modes of the bath at the cost of introducing this new bath-mediated interaction in which 2 spins interact in a time-dependent way. This is a non-local in time interaction. Physically, what it means is that a spin flip emits a bosonic excitation into the bath, which can then propagate and be reabsorbed at some later time. Effectively, this looks as if the spin is interacting with itself in the past. After that, we perform the Hubbard-Swiatkowski transformation, which just introduces these 2 lambda fields, which are the fields that mediate this new bath-induced interaction and the original Heisenberg spin-spin interaction. And then the objects that we're interested in computing are the non-equilibrium Green's functions, from which we can then obtain the relevant expectation values that we care about. Good. How do we get equations in motion for these Green's functions? We do it via least action principle, not on the classical action, which is the one I was referring to in the previous slide, but instead with respect to this gamma action. This is called the two-particle irreducible effective action. And by doing least action principle, we get the full quantum dynamics. Even though this gamma action is the double Legendre transform of the original generating functional, it's more useful to write it as in this second line here, which is actually a loop expansion. And this final term contains all the possible two-particle irreducible, or 2pi, Feynman diagrams. These are diagrams that cannot be separated by cutting 2 lines or fewer. Even though there are infinitely many of these diagrams, we can organize them according to their power in 1 over n, where n is the number of Schwinger bosons that we use to map the spins. Since this is not a physical parameter, as I was mentioning a minute ago, this expansion turns out to be non-perturbative and is what allows us to go into very strong coupling regimes. These 2 diagrams correspond to the Bath-induced and this spin-spin interactions. And I just want to point out that a single one of these, even though they're leading order in 1 over n, actually contain a resummation to all orders in the more conventional Feynman diagrams that you would see in a perturbative expansion. Having done this, we actually do the least action principle, and we get the equations of motion for the various Green's functions of the system. Generically, they look like this. They're integral differential equations of motion. It turns out that there are 15 of these equations that are coupled between them, so it's a rather complicated system, but with enough care, it can be numerically integrated, which we did. But before showing you results, I want to compare our theory with some other similar theories that have been developed based on this 2pi field theory for spin systems. First, for closed spin systems, there are these 2 papers that develop a 2pi theory for closed systems. So this is in the absence of an environment, no bath. It turns out that when we checked the results that these theories produce for small enough systems so that we can benchmark against exact diagonalization, we find that they fail after a very short time. This failure has been seen in other systems of fermions and bosons. But for spins, we believe there's an additional particularity that causes this failure, which is the Schwinger boson constraint. We believe that throughout our evolution, there are virtual processes that are taking us outside of the physical Hilbert subspaces. And this is because, generically, these 2pi theories can only be initialized with Gaussian initial states. These are states that only have non-vanishing correlations for single field and 2-point correlation functions. All the other ones vanish. And so, even though to satisfy the operator constraint, that is the Schwinger boson constraint, we should have that this whole hierarchy of identities should be satisfied, but the initialization of the system with a Gaussian state actually means that only the expectation value of the constraint is satisfied, but not the higher order moments. So this, we believe, is a source of failure in the closed version of these theories. But now that we have introduced the environment eventually will wash out the properties of the initial state, meaning that we might be able to avoid this sort of failure by going to open systems rather than closed. There is another paper that has done a 2pi theory for open quantum systems, which is actually by the organizers, and Hassan Hossein Abadi was supposed to present, but unfortunately I was told he won't be able to be here. In this paper, they formulate a similar 2pi theory for spin systems. They include disorder, so in that sense it goes beyond our theory, but most of the results that they report are restricted to the Markovian regime. And the way you can see that is that in equation 6 of their paper, they introduce this Bath-mediated interaction, which is time-independent, meaning that it's actually Markovian. The system has no memory, and it's not until towards the end of the paper, equation 109, where they have a more general, actually non-Markovian interaction. Good. That being said, I'm finally going to show you some results. The first thing that I'm going to show is plots of the coherence of our spin in the spin boson model as a function of time. the way we get the coherence is just the length of the block vector. 1 means it's a pure state, and 0 means it's a maximally entangled state. The key thing here is that for certain regimes of strong coupling and low bath cutoff frequency, you can actually see initial decoherence, but later recoherence or even localization of the purity of the spin, which proves that we can indeed reach the non-Markovian and the non-perturbative regime of the spin boson model. Now, we benchmarked the results of our theory against numerically exact methods for many, many, many different parameter sets. Generically, they look kind of like this. The solid line is our 2pi derived results, and all the other symbols are the various benchmark methods that we employ. It's not perfect, but it's rather good. And the key thing is that although the numerically exact benchmarks are optimized for very specific corners of parameter space in which they are applicable, but not outside of that, our Schwinger-Keldysh plus 2pi theory actually covers a very large volume of parameter space. So it's a much more flexible method at a still reasonable polynomically scaling computational complexity. The only corner of parameter space where it doesn't seem to work is here, the ultra-low temperatures and ultra-strong coupling regime, where the results are qualitatively okay in behavior, but definitely not quantitative. And the reason we see failure here is that this is precisely the corner of parameter space in which the spin boson goes into, or it transitions into a different quantum phase, the localized phase. This is a phase where the initial conditions are not actually washed out, they are relevant, and so that mechanism that I mentioned in the previous slide of the unsatisfied Schwinger boson constraint is much more relevant, and we believe that there's still a lot of research to do here to be able to get good results in this specific range of parameters. With that, I come to my conclusions. We developed a non-perturbative method for open quantum systems that can reach strong coupling and the non-Markovian regimes. It can access 1 spin and 2 spin correlations. I didn't mention this, but you can check the paper for that. It works for arbitrary spin length. It scales polynomically with the different dimensions. And it mimics numerically exact benchmarks in a very large area of parameter space, unlike the more specialized and optimized standard methods for non-Markovian systems. There are additional things in the manuscript that I invite you to check out. You can find it on the archive or on our group website, along with all our other publications. With that, I come to the end of my talk. I hope you found it useful, and if you have any questions, I'll do my best to answer them. Thank you.
Thank you. Questions?
So, thank you for the talk. I have a lot of questions. I'll try to just ask one. I don't remember, I read this paper at some point. How do you implement the constraint somehow, or you just assume it's a conserved quantity, so it's conserved by 2pi?
Yeah, that's a great question. It turns out that the symmetries of the action do ensure that it's a conserved quantity. So in principle, we don't need to add anything else to the theory to conserve the number of bosons. However, what we need to do is have an initial state that actually satisfies the constraint. The fact that we are only allowed to use Gaussian initial states, and I just want to mention this is a general feature of quantum field theory. It's not just our implementation. But the fact that we're restricted to Gaussian initial states means that while we are satisfying the constraint in expectation value, the rest of the hierarchy is not satisfied. And thus, this is an additional method by which we can see some failure of the technique. This is related to very mysterious stuff like eigenstate thermalization and things like this, which I don't quite understand yet, but it's a good avenue for future research.
We have time still for a quick question. Someone?
Hi, thank you very much for your talk. I'm curious in the part when you mentioned that the fact that you use N, that's the number of Schwinger bosons, determines that your method is non-perturbative. How does this happen? How do you know your method is rather exact and non-perturbative?
Right, okay. So we can all agree that N is not a physical parameter. It's just a detail of how many bosons we pick to map the spins. And it turns out that any number we pick, 2, 3, 4, whatever, works. We can map any spin length with any number of Schwinger bosons. So when we go look at our diagrams, each diagram will have a particular, it's proportional to a particular power of the coupling constant, which is a physical parameter, but it's also proportional to a particular power of 1 over n. Okay, as long as we keep track of 1 over n, we can see what power these two diagrams are proportional to. There's infinite many of these, but the higher order ones will scale with 1 over n squared, and so on. Even though our n is not very large, it turns out to be 4, not 2, for very technical reasons. It has been shown that 4 flavors of real bosons, or 2 flavors of complex bosons like we have, is enough to converge to the large n limit. So I guess we can maybe talk more about this offline, but it all has to do with the fact that it's a non-physical parameter that we're using for our perturbation theory that allows us to go into the actual non-perturbative regime.
Thank you again, Felipe. For a quick announcement.
We realized that, we had to make a swap in the presentation sessions of tomorrow and Monday, and this swap hadn't been announced. So this is, you also received an email today about this. So if they at the very first announcement you were tomorrow, you're actually on Monday and vice versa. So be aware of this. I mean, if you in doubt, check again the updated calendar on the website. Sorry for the swap.
So now we continue our section. I invite now Gianni Aupetit-Diallo. Thank you, Gianni.
About the 15 minutes, including questions. Yes, amazing. Okay, so hello everyone. It's a real pleasure to be there. So thank you for the organizer for giving me this opportunity to present our work. Okay, let's do a little step back and go back to Markovian dissipation. I have the feeling that it will look like a baby model, a baby approach when you look at the president talk, which was quite amazing. But okay, I will try to convince you that it is its strength. The strength of this approach is indeed its simplicity. Okay, and I'm working at SISSA with Mario Colura so far on open quantum systems. Okay, so this method is called time-dependent GG for generalized Gibbs ensemble. Let's talk a bit before on what is a generalized Gibbs ensemble and a Gibbs ensemble. Keep in mind that these are oversimplification. If you want to really characterize these ensembles, you will have to go back to entropy, maximization of entropy. It's just to give a flavor on the quantity that I will discuss today, the notion that I will discuss today. So, okay. First, the GG. In a general quantum system, chaotic quantum system, you have one conserved quantity. So if you want to describe thermal equilibrium states, you will have to deal with this one quantity. This is the Gibbs ensemble. It's somehow the whole system is acting locally on the subsystem as a thermal bath, making it to locally relax to this Gibbs ensemble. And on the other hand, if you consider integrable models, you will have, by definition, an extensive number of conserved quantity. And now, if you want to describe equilibrium states, you will have to deal with all these different quantities. And this is the generalized Gibbs ensemble. And now, the whole system is acting locally on the subsystem as a non-thermal bath, making it relaxing to this generalized Gibbs ensemble. Okay. At this point, we can make a sloppy analogy with board games. On one side, you're playing the Monopoly. And if you want to achieve your target state, which is winning, you will have to deal with roughly one quantity, the money. And on the other, you're playing like a role-play game, and you have to deal with an extensive number of quantities, statistics, inventory, whatever, to achieve your target state. Okay, but now, what happens if we weakly break this integrability? Here, we will weakly break this integrability by adding small dissipation. In this regime, the system undergoes separation of scale between the fast unitary dynamics and the slow dissipation. And it has been shown that in this regime, you can track the evolution of your system with the generalized Gibbs ensemble. And it's somehow like if your dissipative events are slow enough, you let the time to your system to locally relax to this generalized Gibbs ensemble between each event. Okay, but why are we interested in such system? First of all, in this particular regime, the system undergoes very huge simplification in the Limblad equation, simplifying to master equation, which means that we can solve it. It's so simple, we can solve it exactly. Solve it exactly for a huge variety of systems, and also a variety of dissipative effects, and all at the same time. You can consider like gain, loss, dephasing, incorrect hopping, what do you prefer, and all at the same time, and still obtain an exact solution. So it's quite powerful. Okay, well, if some of you are knowledgeable on this kind of approach, you can argue that there is already a lot of work on the topic. So what can we brought into this topic? Well, when we started to work on this, there was a huge debate on the validity of the method, because you can argue that, okay, if I assume a finite time of relaxation tau, it gives a constraint on the event rates. And okay, it is known that the relaxation to the GGE is not exponential, it's algebraic. So from scratch, when you look at the method like that, it's not even clear that you can take a gamma small enough for the method to work, and also to be physically relevant to describe something. So the idea is to really like show that this method works, and also obtaining this rapidity distribution, so the quasi-momentum distribution, can be done in many ways. So we also have to show that we can go further than that and rely on this method to compute more convoluted setup, let's say. Okay, so with that in mind, my plan is twofold. I want to convince you that the method works, is valid and accurate. And I want to show you also that we can go further. And for that, I will consider a more convoluted setup and consider transport with an initial inhomogeneous setup. And to do the comparison, I will do the comparison with exact tensor network computation. And this is the main strength of this work, is that we go to unprecedented number of lattice sites in the tensor network computation to be sure that, okay, it works, without a doubt. Okay, so now, the model. As I said, we consider Markovian dissipation with the Limblad equation. For the unitary evolution, we consider hardcore bosons, so an XX Hamiltonian. And again, we are at adiabatic dissipation and slow dynamics to let the time to the system to relax, to locally relax to this generalized Gibbs ensemble between each dissipative event. I will skip the technical details. If you want, you can ask me some question. Would be my pleasure, or discuss after. Just remember that all this assume that we are restricting the dynamics to a Gaussian manifold. So it's a strong assumption, but I will show you that, okay, it's pretty good approximation, and we are really well approximating the real state. Okay, so now on the results. If you solve the system, okay, whatever. If you solve the system, the master equation, sorry, you obtain an exact solution for the rapidity distribution, which is a function of the mean density, the steady state density, a modified Hilbert transform, the H, a modified Hilbert transform of the initial density profile, okay, and some functional f, which depend on the dissipative parameters. So there is multiple things to say at this point. First, it's a very powerful formula because you can obtain all the different, like for instance, the Hilbert transform very fast via fast Fourier transform, and the functional is simple enough to be computed, to be integrated very easily. So it's a very powerful, very fast formula. It's also quite general because we've shown that if you add on top of the gain and loss, for instance, incoherent hopping, dephasing, this formula remains the same. You just have to change the function f. And it's also very versatile. You can choose whatever you want in terms of initial density profile. Here we choose a thermal initial state, but you can choose an EL, an L, dimer, or whatever. And okay, so I show you what we get in terms of results on the right. Multiple plots, we can discuss that after if you want. What we can directly see is that between the dots, which are obtained with this formula, and the solid line, which is obtained with exact tensor, 40-site tensor, exact tensor network computation, there is a very nice agreement. It was wonderful, very happy with that. And on top of that, we've shown that if we increase the number of sites, the solution becomes number of sites independent, so we really reach the high number, the large number limit. So, okay, very nice agreement, very happy. Let's characterize a bit and say a word on this validity. For that, to quantify this validity, we use relative error, which is defined as such. And okay, looking at these plots, we can see that the agreement is indeed very nice. We are on the order of like 0.001, 0.01, and not even for like super small gamma. Like we can choose gamma of the order 1, depending on what you want to do at the end. You still have a very good agreement. We also find back the gamma T scaling. It's just nice. It's not super surprising, but it's nice to get back the scaling. And in terms of limitation, we show that, okay, let me go back a second. Yeah, the method works a bit less when there is only, wonderful, when there is only gain or only loss, which is not a huge drawback in the end because you just have to add a tiny bit of gain or a tiny bit of loss to increase a lot the accuracy. This culminates for the balanced gain and loss when the accuracy becomes basically negligible. And okay, last, a little word on the temperature. If you increase the temperature, you gain a lot in terms of accuracy because the state becomes more Gaussian, and then you best deprive your states in the end. Okay, so this was on the homogeneous setup. I hope I convinced you that it works. I will now go to a more convoluted setup and consider transport. The usual way to consider transport in integrable system is using GHD. I will not go too much into detail, but if you want, we can discuss that. And we assume that it should work because we only weakly break the integrability. And indeed, it was working. And for doing so, we used, to solve this new system, we used the split step method, which means that first we plug in transport, okay, compute a new state, and then plug the dissipation with the master equation I just showed you. This is one time step, and then we iterate to obtain the full dynamics, basically. It's pretty simple. Okay, and on the results, we start with an initial domain wall, a sharp right-left imbalance. And we do two different kind of comparison. One with 100 lattice sites in the tensor network and one with 200 lattice sites. This time the dots, sorry, this time the dots correspond to the tensor network exact computation, and the lines correspond to the split step method. And again, we have a very, very nice agreement. We were very happy with that. So it shows that we can use this approach also to go to like more complicated setup, and we can really rely on this simple method to go further than just computing the rapidity distribution. And I will stop here with the results. Just saying a tiny word on what we can do after. There is a huge limitation for now. Is like we are limited to non-interactive system. It's not a theoretical limitation, it's just a technical limitation for now. So we are working on this. And we are trying to match the quasi-particle picture and this TGGE to compute entropies, entanglement entropies, and we are very close from publishing this. I hope next time we'll have time to discuss that. Okay, and I will stop. Sorry for the rush. Thank you.
Question?
Thank you. So if you go back like to the first results that you showed, where you have like your density, that one, yeah.
Mm-hmm.
So in the upper left panel, there's like a slight deviation. So is that because of the thing that you commented that you had only loss or only gain, or is it because something else?
Sorry. It tends to overestimate when there is only loss and underestimate when there is only gain. This is a common effect, and this is the same effect because of particle Hall symmetry.
Okay.
And it's basically because the states you are describing is like less Gaussian. So yeah, that's yeah.
And then one quick, so what is the scaling of your method? As
scaling?
A function of the time, for instance.
It's scaling gamma. Everything is in gamma t, gamma, which is the sum of the different DC.
No. I meant like the computational complexity of your method.
This is a very good question. This is I was not doing the tensor network computation. It's my supervisor who was doing that. So yeah,
No,
I have
thank you.
no idea. Never mind.
Thank you once more, Yanis. Thank you. So now our next speaker is João Paulo Neves Azevedo Machado.